Throughout the section, we discussed different undersampling techniques. In this video, I want to discuss how we should correctly set up a classifier utilizing undersampling. You've seen throughout the section that we take up the original dataset and we always divide it into a training set and a test set. In the train set, we're going to train the algorithm and we leave the test set just for model evaluation. Now, we should train the classifier utilizing the undersampled training set. So we would only undersample the train set and then we train the classifier on that portion of the dataset. But we evaluate the performance of the model that we just trained on the test set, and this test set contains the original class distribution. So this is very important. We evaluate the performance on the portion of the dataset that was not undersampled and therefore contains the original class distribution. And this is because when we train our classifiers, we want to use them in real life, and in the real life, the class imbalance exists. So we need a performance that represents a view of what we are going to obtain with this classifier when we use it with our real datasets. So in the rest of the video, we are going to compare the performance of different undersampling techniques on the random forest that we are going to train with cross-validation. We are going to train the random forest with cross-validation in the training set and then evaluate the performance on a part of the dataset that was not undersampled. And to do this with cross-validation, we need to set up the code in a certain way. In this case, we're going to train, as I said, a random forest. We're going to evaluate the performance with the average precision recall score, which, if you remember, is an aggregated view of the precision recall curves. We import the train test split to separate the dataset into train and test. And with cross-validate from scikit-learn, we're going to implement cross-validation. We're going to work with different datasets that come baked into Imbalanced Learn. And from Imbalanced Learn pipeline, we're going to import the make pipeline to set up the undersampling and the classifier within a pipeline object. And this is going to help us set the cross-validation correctly. And then we import all the undersampling methods from Imbalanced Learn. This dictionary is identical to the one that we discussed in the previous video. We have one key per undersampling method, and we set up the undersampling method with certain parameters that we discuss throughout the section. Something important here is that we set up the instance hardness threshold utilizing the same estimator that we're going to use to finally make our predictions. This is the random forest, and this is the best way to obtain the better performance utilizing instance hardness suggested by the creators of this technique. We're going to import a number of datasets. Here we print the class imbalance to become a little bit more familiar with these datasets. And this is the function where we set up the model training with cross-validation. This function takes the training set only and the target corresponding to the train set, and then it has the option to take the undersampler. And here we set up undersample equals none because we want the function to work as well with the original dataset. In the first step of the function, we set up a random forest with some parameters. Because some of the undersampling methods require nearest neighbors, and nearest neighbors is sensitive to the scale of the variables, we are going to also scale the variables with the min-max scaler. And then, if we enter the function with undersampler equals none, means that we're going to train a model on the original dataset. So here we want to set up the model equals to the random forest that we set up in this line of code. But, and here is when the magic comes in, if we are going to perform undersampling with the make pipeline function from Imbalanced Learn, we first are going to scale the data, then we're going to perform the undersampling, and this is because we scale the data in case our undersampling is using a nearest neighbor algorithm, and then we train the random forest. So this pipeline is going to perform these 3 steps one after the other. Then we're going to pass the model, which is a pipeline in this case, or just a random forest if we're not using undersampling, to the cross-validated function from scikit-learn. So here it takes the model, here it takes the training set, the target, we need to specify which metric we want to evaluate, and the cross-validation fold. And doing it like this ensures that scikit-learn will first separate the dataset into the 2 folds that it's going to use for training and leave out the fold that it's going to use for testing. Then it's going to scale the dataset based on those 2 folds. Then it's going to resample only these 2 folds. And then it's going to train the algorithm on those 2 folds. And finally, it's going to measure the performance on the fold that was left out and that was not undersampled. So we get a view of the model performance in a portion of the dataset that contains the original class distribution. So here a common mistake is to first undersample the dataset and then perform cross-validation. And if we set it up this way, then the cross-validation will output performance metrics that were calculated on the resampled dataset. So it is important to pass the undersampling technique to the cross-validation method like we do here. Finally, we print the results. The results are stored in the CV results. You can find more information in the scikit-learn documentation. But the important thing is that we have 3 values because we did 3-fold cross-validation. So we will have 1 performance metric in each fold that was left out at each round of the cross-validation. So we can determine the mean, but more importantly, we can determine a standard deviation. So we get a better view of the performance of the model with the mean and an interval of error. So this function will output the mean and the standard deviation of the performance of each model. Now the rest of the code is very similar to the one that we saw in the previous video. We are going to start 2 dictionaries to store the mean value of the performance and the standard deviation for each dataset, for each model with the different undersampling techniques. So here we initiate a new dictionary for the dataset that we're evaluating in the loop. We load the dataset with this function. We divide the dataset into train and test. And for the rest of the notebook, we're only going to use the train set and we're going to ignore the test set because we're going to evaluate cross-validation. We train the model then on the dataset without resampling with cross-validation. So we call our function and we pass just the train set and we leave undersampler to none. And here we store in the dictionaries the mean precision score and the standard deviation. And then we're going to loop for each undersampler in the dictionary and we run the same function, now passing the undersampling as a parameter to the function. We store the results. Here you're going to see the performance for the different models. And now, like we did in the previous notebook, we can print the average precision score for each dataset, for each model trained with the different undersampling techniques. And for example, for the first dataset, the car evaluation dataset, we see that NEAMIS tends to produce a better performing model. And here it is important to see that the error bars do not overlap. This means that there is a significant increase, for example, compared to the original dataset, as opposed to this bar, for example, with this bar, that are overlapping, and then it means that the increase is not significant from a statistical point of view. For the E. coli, the full dataset seems to produce the best performing model, and the undersampling methods do not seem to help. For the thyroid-sick dataset, we see that condensed nearest neighbors tends to improve the performance of the model. For the arrhythmia, the models return quite a big error, so it's very difficult to say that one undersampling technique has produced better results than the other, and the same for the ozone dataset. So to conclude, different undersampling techniques work well with different datasets, and we need to be careful of how we set up the classifier using undersampling within a cross-validation loop, because we want to train the model on the undersampled data, but we want to test the model on a portion of the data that contains the original distributions. If there is anything that you need to take out from this video, this is it. We train on the undersampled, we evaluate on a dataset with the original distributions. That is all for this video.